You are using the computer audio. Okay. Recording, it says. What am I supposed to do now, doggone it? I thought I was supposed to say start. Yeah, here we go. Start video. Hey, Calvin's on here already. All right. No, Calvin is connecting to audio. Can't hear you yet. He can't hear me yet, but he is connecting. Now I'm going to pin video. Okay. That's pretty good, I guess. Needs to be bigger though, doesn't it?
That's all right.
I need it to be
Mr.
bigger.
Griffin.
Hello. I want this to be, hey, yeah, there's Mohammed. Yeah, good deal.
Yep.
I want this to be big on my screen. What am I doing wrong here? Launching, it says.
There should be 3 dots in the top corner. If you click it, you can click pin video.
Okay, 3 dots in the corner. I see 3 dots. Let's click that. Oh, no, I don't think that worked. Let me keep, I'll fumble along. I'll get it here, Adam. Just, I see Adam there. Yeah, there's the 3 dots that Adam's talking about. Pin video, we're going to try that. I just need it to be bigger. What if I click that little square thing? Yeah, now that's more like it. Hey, look at here. I've got Calvin, Kristen, and Mark, and Zach, I think, and Mohammed. Let's see who else I have here. And looky here, I've got Adam, Kristen, Levi, Mark, Tyler, Ben, Calvin, Zach. Pretty good crowd so far. Okay, well, we have about 3 minutes before we start. It's so sad, but this is, I think, our last physics wonderful lecture here. And Sunday night, I'm going to post your final exam.
About what time Sunday should we be expecting that?
Whatever time I can get my daughter to help me. Probably the afternoon sometime.
Okay. Yeah, I was just like, just want to know, just so I wasn't like checking every 5 minutes unnecessarily.
Yeah, it'll be, I don't know. We'll just have to play it by ear, I guess. You'll have plenty of time to work on it. That's wouldn't be a problem. Okay, well, we've got a good class and it's almost 1 o'clock.
I just logged in. Were you talking about the exam?
Yes. Oh, okay, yeah. I'm going to post your final exam probably Sunday afternoon. Was that Melissa?
Yes, sir. And
Yeah, hi,
so
hi, Melissa.
Hi. So what's the deal with that?
You have till Wednesday night to do it and submit it to Blackboard. I'm going to grade it on Blackboard. And you guys have been doing that before somehow. And some of you have actually sent stuff that I can read, which I appreciate. Okay, now let's see. We need to get started. It's almost 1. And I asked you to work on, I think it was 1531, wasn't it? Is that what it was, 1531?
Yes, sir.
Yeah. Let's just work that to death, shall we? I'm going to take that and just work it and work it and work it. Let me find it here in the book. Just a minute here, 1531. Totally organized. And maybe we can say some things that would help you on your test, you know, some review type stuff, but we'll do this. Now, okay, now this has got, this has got a 20 microfarad capacitor. This problem here has a AC source, and all they've got is a 20 microfarad capacitor. Okay, that doesn't bother us. We can handle that. And now let me write this source. This source is 100 volts, sine of 200 pi t. There you have it. So you see, that's your maximum voltage right there. The maximum is 100 volts. You can see that. Now this is it's 20 microfarad. This is a 20 microfarad capacitor. Okay, we're going to do that. That's part A. Then we'll do part B, and then we'll do part C. And we'll just play with this thing here for a while. What you've got to have is the capacitive reactance. You know the name of it. It's called capacitive reactance. And it is 1 over omega C. I think we showed you that the other day. I tried to show it to you why that is. Now we need to get this omega. Now the omega is, well, that's the 200 pi. That's what that is. And it's radians per second. And we know the C is 20 microfarads. So we're going to go 1 over 200 pi seconds to the -1 times 20 microfarads. Okay, I'm going to do that. Here goes. 200 pi times 20 e to the -6. And you have to flip it. You have to get the reciprocal. I'm getting 79.58 ohms. Ta-da! We just figured the capacitive reactance. Now we're going to get the maximum current. Now the maximum current is going to be your maximum voltage divided by your, well, the only ohms you've got is the 79.58 ohms. So we're going to get the maximum current. Here goes. We see the maximum voltage is 100. We know what it is. It's 100. Okay. I'm getting 1.25 rounded off to 7 amperes is the maximum current. Now, if you wanted the root mean square current, I'll talk to you about root mean square some more here in a minute. I tried to explain it the other day, but I don't know if I did that great a job. But we'll try again. For sinusoids, it's 0.071 times the maximum current. Not everything is a sinusoid. There are other kind of waveforms. There are sawtooth, for instance, and square wave, and a million other kind of waveforms besides sinusoidal. But for sinusoidal waveforms, the root mean square current is 0.7071 times the maximum. And in this case, it will be times 0.7071. I'm getting 0.8886. What would be the units? Well, it's current, it's amps. That's just a number. There's no dimensions to it, or no units. You just got current. Yeah, there you go. Hey, we just got the root mean square current. And I think that's the right answer, by the way. If you look up the answer in the back, I think the book says 0.89. They just rounded off.
Professor, that 0.7071, is that 1 over the square root of 2?
Yeah. No, I think it's 2 over the square root of 2, isn't it? Maybe I'm wrong. No, you're right. It's 1 over the square root of 2. Let me double check that here, just a second. Boy, Jove, that's it. It's 1 over the square root of 2. Good going. Okay, well, we're all done with part A. That was fun.
Mr.
Now
Griffin,
let's do part B. And we'll put a little A here on all of that. That was loads of fun. That was part A. And now we're going to do part B. Now part B, they got rid of that and they put an inductor in there. Same deal. It's just you've got this inductor. Some people call it a coil. There are many kinds of inductors. There's solenoids, for example. And there's circular loops. There's all kinds. But anyway, it's some kind of a inductor. And if you read the problem, it says it's 20 millihenries. 20 millihenries. Okay. Well, what are we supposed to do? Find the inductive reactance? I think that's it, guys. We're going to find the inductive reactance.
Mr. Griffin,
Yeah,
I have a question.
go ahead.
On part A, on the capacitance reactance, the
Yeah.
1 over omega C,
Yes.
what is that in the middle? It says 200 pi something.
Yeah,
That-
that's 200 pi seconds to the -1.
seconds. Okay.
Yeah, thank you for asking. That
I
is
thought it was
the,
a 5. I was wondering where that came from.
yeah, sometimes I write my seconds like this. And sometimes I write it the other way. But now you know. Thank you for asking. We got it. Okay, well, let's do this one now. Now here, we're trying the what they call inductive reactance, and it's equal to omega L. That's not a W, guys. That's an omega. It's a Greek letter omega. The capital omega looks like this. Hey, we already used that for something. What do we use that capital omega for?
Ohms.
Ohms. It stands for ohms. Yeah. Well, see, the capital omega stands for ohms. But the little omega, it's got units of seconds to the -1, and it stands for angular velocity is its name. The book sometimes calls it angular frequency. Okay, well, here we go. We know it's 200 pi seconds to the minus 1 times L, and L is 20 millihenries. Okay, I can do that. That would be 200 times pi times 20 e to the minus 3. I'm getting 12.566 ohms is the inductive reactance. Yay, we got that. And by Jove, is that what we were supposed to find?
We need to find the
No, we're not done yet. We're supposed to find the RMS current. Well, we can do that. Here we go. We're going to find, we found the RMS current with a capacitor. Let me make some space here so we can do it. Okay, now first we're going to find the maximum current. Now the maximum current is the maximum voltage divided, in this case, we're doing part B, divided by the inductive reactance. Maximum voltage is 100 volts. Inductive reactance is 12 point, blah, blah, blah. And supposed to put volts in brackets, I guess. Okay, now we're going to get the maximum current. Here goes. I'm getting 7.958 amps, but that's not what they wanted. They wanted the RMS current. Now the RMS current is 0.7071 for sinusoids times the maximum current. So just multiply this by 0.7071 and you'll get 5.627 amps. And the book says, well, the book says 5.6. Let's don't fight over it. The book says 5.6 amps. They're just being lazy. It's 5.627 is what it is. So we found the RMS currents on both of these, part B. Do you understand the RMS is what you would measure? If you put a AC ammeter in here, I'll make you a little symbol here for an AC ammeter. You know what they read? They read the RMS currents.
Is that just because it's alternating current?
Yes, it's alternating current. And an AC ammeter reads the RMS value.
But if it was a DC circuit, then it would be the 7.9.
Yes, exactly. Yeah, that's right.
So alternating current puts out less current for higher voltage, or
I didn't quite understand your question. So
or just
rephrase it.
So, well, because DC current would put out the 7.9 amps, but an alternating current circuit would put out the 9 or 5.6. But is that 5.6 just what it reads, or is it actually?
Okay, I think I can answer your question. If you had a DC current, where's our RM? Is this? Yeah, here we go. If you had a DC current of 5.627 let me write that for you.
Well, if we were doing this exact circuit and it was a DC circuit rather than being AC,
Yeah.
then it would put out 7.958 amps, correct?
No, it would put out, to get the same power, you would have to have 5.627 amps. Here, let me draw it for you. This is an important thing to know. If you had a 100-volt DC source, oh no, I need to do this with the resistor. I forgot a little fact. Capacitors don't use any power. I mean, they do, but the average power is 0.
Okay, so it would change power values.
Yeah, to get the same power, you have to have the RMS value, but you have to have a resistor, because remember, there is no average power with a capacitor or an inductor. We're going to do the resistor now, part C, and then it'll make more sense to you, I hope.
Are we
Okay.
measuring the current with like a CT?
CP?
A CT, like a clamp on?
Oh, they have those kind. Those kind of AC ammeters that it's like a coil that wraps around your wire. That's what you're talking about, I think.
Yes.
But
So we're not.
they also have the inline AC ammeters. We have them in our lab. But to use them, you have to break the circuit and you have to insert the AC ammeter and you get a reading, but it reads RMS. It doesn't give you the maximum, because see, the maximum goes one way and then it turns around and goes the other way. It gives you the RMS.
Okay.
I don't think I've lied to you anywhere here so far. Let's do part C, and then I'm going to try to play with these same values of resistance and capacitance and inductance for a while, and maybe we'll catch on. What we're going to do now is the resistor. Okay, here we go. Same deal. We have 100 sine of 200 pi T AC circuit. And we're going to hook it up to a resistor. And if you read it, it says 50 ohms. We're doing, if somebody tuned in late, we're doing the chapter 15, number 31, and I just want to show you some things about it. Okay, now to get the maximum current, that's going to be the 100 volts. See, that's the maximum voltage right there. And you guys understand it goes up 100 and it goes down negative 100. It's alternating. But the maximum current will be 100 volts divided by 50 ohms. And I can do that in my head. Hey, time to show off a little bit. I'm getting 2 amps. Now that's the maximum current. But now if you want the RMS current, that's going to be 0.7071 for sinusoids, and that's what we have, times the 2 amps. I'm getting 1.414 amperes. And that is the answer. Well, no, the book just rounded off. They're a little bit lazy. They said the answer is 1.4 amps, but we'll forgive them. That's pretty good. Okay, well now let me talk about this RMS thing one more time. See, power there's instantaneous power. That's a little p, and it's I squared R. And then there's big P, average power. Well, instantaneous power depends on your current, and it varies. It's varying just like this. In fact, in this case here, I'll tell you what it is. The instantaneous current is a it's 2 amperes times the sine of omega t. And if you plotted it up, it's a sine, and it goes, there you go. I tried. Yeah, it's pretty close, like that. And it goes up to plus 2 amperes, and it goes down to minus 2 amperes. See, that's the maximum value. But when you try to get the instantaneous power, you have to square the current. This is the current. I'll put little eyes on it so you know we're talking about current. But when you square that, you get something else. Now I've got some other colors here. Let me try this. I wonder if this green will show up. When you square this, here's what you get. Ooh, that's coming out pretty nice. You get a peak here and a peak here. Wait a minute. No. When you square negative, it comes out a positive, doesn't it? Yeah, I did that wrong. Okay, now let me get this right. This goes like this. Yeah, like this. Yeah, what I'm plotting right now, I'm plotting I squared. See, if you multiplied I squared times the resistance, 50 ohms, you would get the power at any given instant. And the power in a resistor is never negative, it's always positive. And you can see what the average would be. The average is just right down the middle. That would be the average of your I squareds. This value right here is your it's your I max squared. I don't know if you guys can read that. Let me write that with the black, nice and thick. This top value here is I max squared, which in this case would be 4 amps squared, because I max is 2, and this here is 0. It goes from 0 to I max squared. Can you see that the average, the average of your instantaneous currents? Why don't we put a bar over there? People put bars over things to show the average. It's 1/2 of I max squared. See, there's I max squared right there. In this case here, it happens to be 4. But 1/2 of it would be right smack dab in the middle. That's your I max squared. So if you wanted the root mean square, here we're going to get it for you. Here we go. The root of the mean of the square. Well, that's the square. And the mean of the square, this is the square. If you want the average or the mean, that means average. Mean means average. If you want the average of the squares, it's 1/2 of I max. Now, if you take the root of that, that's what we're going to do. We're going to take the square root of both sides. And here's what you'll get. You will get what they call the root mean square current. It'll be the root mean square. It's the root of the mean of the square. And here's where this 0.707 comes from. If you take the square root of 1/2, you'll get 0.707. If you don't believe me, take your calculators, put in 1/2, take the square root of it, and you'll get 0.707. Now, when you take the square root of this, you get I max. That's where that comes from. See this 0.7071 I max? There's your I max. Well, if you didn't understand at that time, read your book. Let's move on. But any comments or questions before we move on?
It made a lot more sense that time, to me at least.
A
a lot more
little more?
sense.
Good. I'm glad. Hey, we got a great group. I see Nathan, Mohammed, Melissa, Levi, Kristen, Jeff. Jeff is down here twice. Now, they explained that to me once, but I don't remember. Ben and Adam, Logan, and Chris. Spellings. Got a great group. Okay, now here's next. Here's what's coming next. We pretty much did 1531. I just want to combine those same components a different way. Let's combine them like this. This will be fun. What was that? Was that the 20 microfarads? I think it was. And this was the 50 ohms. And let's have the same. Let's have the same. Maximum volts is 100, or was it 200? I think it's 100. Wasn't it? Yeah.
Yes, yeah, it was 100.
And the omega was 200 pi. So there's your AC source. And we're just going to play with that one. Now the best way to do these is to draw the impedance diagram. Now remember the way that goes is you put your resistance here. There's your resistance, it's 50 ohms.
So,
Go into there for
You need the inductor?
yeah, so Dominic.
that's a resistor.
I know,
Yeah.
but do we need an inductor?
No, we're just going to do this one, and then in a minute we'll do an inductor too. But we're just going to do this one. This will be fun. You'll love this. Now the capacitor's got to be down here, but I forget what the capacitive reactance was. I'm going to have to do it again.
0.57.
Say that again.
79.57
Oh,
ohms.
okay. It's a little longer than 50, isn't it? It's more like that. It's 79.7 ohms.
57.
57.
Yeah.
And not that I don't trust you, but I want to double check and make sure that we got that right. So I'm going to plug that in. I'm going to take 200 pi. And then I'm going to multiply by 20 e to the minus 6. Take the reciprocal. Yeah, 79.5. Good going. 79.5. 77. Excellent. We did it. Notice there is no inductive reactance. There's no inductor. There's no inductive reactance. That doesn't bother us. Now you could actually measure this, guys. Let me actually measure it. Now this is supposed to be 79 something. So that would put me to right here. I'm actually going to measure this. And this is supposed to be 50. So that would put me to right there. I've actually done those to scale. Now what we're going to do is these, the way they add like vectors. And this is going to be the impedance right here. And I can get that. It's going to be 50 squared plus 79, blah, 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 squared, square root. Okay, here goes. We're going to get the impedance now. For this circuit, we're going to play with some different circuits and learn some things, maybe. Well, I got an answer. Did you get an impedance of 93.98 something ohms? And I'm going to wait for an
Yes, sir, I got that.
Yay, good. There's two of us. Good deal. And this here is important. This is called the phase angle. That phi there is called the phase angle. It's the angle between, it's the phase angle between the source and the current. Because see, the current will be right along here. And we can get the current here in just a minute. But the current, the voltage in the resistor and the current in the resistor are in phase. Okay, let's get the current. Here we go. I'm going to get, now this is going to be the maximum current. That's going to be the maximum voltage. Same source we've been having, divided by the impedance, which is 93.982 ohms. And we're going to get the maximum current. Here we go. I'm getting 1.064 amperes AC current. That's the maximum current in this circuit. Current goes back and forth, but the maximum is 1.6, and then it turns around and goes the other direction, goes 1.064 amps, then it turns around. And it turns around how many times a second? Let's figure that. That'll be interesting. See, omega is 2 pi times the frequency. And we know what omega is. It's 200 pi. They gave us that. So if you solve for the frequency,
Yeah, simple 100 hertz.
I think it's 100 hertz. I really do. I think it's 100 hertz. In other words, it's going back and forth 100 times a second. This is AC current that's changing 100 times a second. Interesting. Now, if you wanted the root mean square current, see, that's what you would measure if you measured it with an ammeter. That's 0.7071 times 1.064, and that is 0.7524 amperes. So now we have the RMS current. Now we're going to get the power. Now, before we didn't have any resistor, and capacitors don't have any average power. They have power. They store and they return, store and give it back. Provide power, store power. But the average is 0. The average power on an inductor or on a capacitor is 0. But this has got a resistor, and the average power in the circuit is it's RMS I though. That's why, it's another reason why this RMS thing is so important. It's RMS squared, it's I squared R. You've seen that before. You use that formula with those light bulbs. Remember those light bulbs that we worked several days? We had those. I kept bringing them in, hoping that you guys would catch on how to work those. Hey, that would be a
Almost
good.
shocked yourself.
Yeah, you were hoping I would shock myself. That would be a good thing to study for the final. Those light bulbs. You remember those light bulbs we had? We had some light bulbs. And we connected them up to an AC source, and we had to find the current and all that. You didn't know it at the time, but you were doing RMS. You were doing RMS. You didn't know it at the time, but that's what you were doing. Okay, well, we're going to get the average power. Now, we got the RMS current here someplace. Here it is. It's 0.7524. We're going to square that times 50, and we're going to get our power. Here goes. All right. Square that times 50. Did you get 28.3 watts?
Yes.
28.3 watts. Yay. Logan, you got that, didn't you, Logan?
Yep.
I got it as well.
Yep. Yep.
Yeah.
You said. I think you said yep. Now there's another equation for average power. Now let me show you this. I think it was Kristen that wondered, well, what good is that equation when you have this one? Well, it's not much good, but it is a way of checking your work. So I'm going to check my work. Now the other way is to do this here. Take your RMS current, your RMS voltage, times the cosine of your phase angle. Now we have no, we don't have the phase angle. Look at here. But we can get it, can't we? You guys all took trigonometry. If you come over here 50, and that's 93, then you take the arc cosine of 50 divided by 93.982. Take the arc cosine. Guys, I got 57.86 degrees. I did this to scale. That kind of looks like 57.86, doesn't it? I did it to scale, and it looks pretty darn good. Okay, let's try this and see what happens. Now, the RMS current is 0.7524. Now, the RMS voltage, see that's the maximum. The RMS voltage would be 70.71. Do I need to explain that? I guess not. You got it. So multiply that by 70.71, and then multiply by the cosine of phi. I ran out of room there, but we got that phi. It's 57.86. Put this in your calculator. we're doing this really just to check our work. It should come out to be 28.3 watts. Let's find out. Here goes. I'm going to try it now.
That capacitor doesn't have resistance, does it?
No,
Okay.
but it has reactance. It has a reactance of 79.577 ohms. That's called the capacitive reactance.
Mm-hmm.
Okay. Now let's see here. I got lost. I'm plugging in this equation here, and I'm hoping to get 28.3. By Jove, if you plug in this equation here, I'm getting 28.3 watts. So you can use this equation to get your average power, or this one. Now, this thing here is called the phase angle. It's the angle between your voltage and your current in your circuit. Let me see if I could draw that for you. Now, the voltage in your circuit is a sinusoidal voltage. I've written it several times, but here, let me write it again. The voltage is equal to 100 volts sine of 200 pi times your time. I wonder if you can read that. Maybe. Yeah, maybe.
Yeah, we can read it.
Yeah, great. Okay, so it looks like this. It goes like that, and it peaks out here at 100 volts, and it bottoms out at minus 100 volts. But what about the current? Well, this is a capacitive circuit, and you've memorized my little thing, Eli the Iceman. Eli the Iceman. We have a capacitive circuit. We don't have an inductive circuit. There's no inductor at all in this circuit. So the current must lead the voltage. Okay, I'm going to draw the current for you now. It's going to lead the voltage, but not by 90 degrees. It's going to lead it by the current. Here's the current. I'll draw that so you'll understand. It's going to lead it by 57.86. See, 90 degrees would peak out here, but this is peaking out. I'll try to fake it here for you. Well, what I'm trying to draw now for you is the current. Now, I don't know the amount. Well, yeah, we know the amount. It's, where did the amount go? The current. Where's the maximum current? I think I erased it. Too bad.
It's 1.064.
Yeah, that's it. Good going. This peaks out at 1.064, I think you said, amps. See, you have to put different scales on here. That doesn't bother us. We can have volts going this way, up and down, and we can also have amps, can't we? And you can have them. You can have a different scale. But what this is, this green thing, did it come out? Yeah, it's green. That's pretty cool. That's the current. We'll put little eyes on it. There's the little eyes. Whereas this black thing, it's the voltage. It's the 100 sine 200 pi t. That's the voltage. Do you see that the current peaks out before the voltage? The voltage doesn't peak out till later. See, time ticks away this way. We're all getting older. You guys are getting older too. I'm getting older. Time is going this way. This is later. But see, this here peaks out earlier. Do you understand? The current tops out on top of that hill earlier. The voltage tops out on the top of that hill later. The current leads the voltage in a capacitive circuit. And in this case, it leads it by 57. If you converted this to degrees, it's 57.86 degrees that it peaks out. Now notice also that the current comes down here and dips down below the axis right there. Well, the voltage comes here and dips down below the axis, but it does it later. How much later? Well, the angle that we're talking about would be 57.86. You guys know how these angles work. See, this here would be 180 degrees. This would be 360. That's the whole cycle. The whole cycle is 360 degrees. Half of the cycle right here, that's 180 degrees. Or you could say pi if you wanted to, and 2 pi, that'd be all right with me. And this right here, that's just pi, or what, 90 degrees, right? So you understand that. Now this is kind of hard to grasp sometimes. That's why they made this phasor diagram. This is the phasor diagram. And look, they've got the phi right here. There's the 57.86. They've got the impedance right here. This right here is the XC, and that's your R. There's a resistance, capacitive, reactance, impedance. They call this the phase angle. This has a name too. This cosine of phi, that's called the, oh gee, it's got a name.
It's called power factor.
Power factor, proud of you. I heard that. It's called the power factor. Now you guys are going to take a course called, it's the electrical stuff. So what is the name of the electrical course that you guys are going to take?
Intro to Electrical Science.
That's it. You're all going to take it. Intro to Electrical Science. And you're going to study the same stuff that I'm teaching you. But when you study it, hey, you'll already know a little bit already. That'll be good. That'll be very good. They call that the power factor. All right, let's change it now and put an inductor in play with it. Any questions before we do? We're going to put an inductor in there and play with it. But is there any questions from anyone? Okay. Let me make some room so we can do it. We finished 1531. We got all the right answers, but we're taking the same power source and the same components. I'm just combining them in a different way. Now this time we're going to do this. Same power source. Now I remember what this was. I think it was 20 millihenries, and this was 50. Did I get that right? 50 ohms. And this is 100 sine of, oh gee, 200 pi t. Now did I get everything right? I think I did. Yeah. Yeah, I think that's all right. Okay, great. Well, we already did this, the inductive reactance earlier, but I forgot what it was. Um,
12.56.
Yeah, was it 12.56?
Yes.
12.56 ohms is the inductive reactance. I appreciate that. Okay, well, we're going to do this circuit. Now, what you need to do is you need to draw the impedance diagram. I want you to draw the impedance diagram. I'm going to be quiet for 1.5 or 2 minutes. I'm going to shut up and I want you to do it, and then we'll do it together. On your mark, get set, go. Draw the impedance diagram. Well, let's see what it looks like. What you should have is something like this. And something like this. But you know, I could do that. I could do that to scale. Here, let me do it to scale. If this is 50, I think I'm going to do this to scale. And then this is I tried to draw that to scale. This is 12.5, 6, and this is 50. Ta-da! And then to complete the impedance diagram, you really need the Z, the impedance, and here it is. We're going to get the impedance now. Square that. It's like vectors. You have to square that. 12.56 squared plus 50 squared. I'm getting 51.55 ohms for the impedance. I'll be glad to go over that if anybody is not happy with it. Okay, now we're going to get this phase angle phi. Here we go. I'm going to take the arc, and you could take the arc tangent. That would work. Take the arc tangent at 12.56 divided by 50. That should give you your phase angle. Now that's the angle between your source and your current, your volts and your amps. All right, here goes. 12.56 divided by 50 arc tangent. Guys, I'm getting 14.1 degrees. Okay. Now let's get the current. Here we go. If you wanted the maximum current, you take the maximum voltage and you divide by the impedance. Okay, well, that's 100 volts, and this is 51.553 ohms. All right, here we go. Maximum current. I'm getting 1.93. Let's just round it off to 4. 1.94 amps. And let me know if that's not right. Now that's the maximum current. Now if you wanted the RMS current, that's just 0.7071 times the maximum current. Okay, let's do that. I'm getting the RMS current is 1.372 maybe. Great. Now let's get the average power. And there's some room here. I just need a little room. And my students can help me if I erase something I need. We're going to get the average power. Now, inductors don't have any average power. They have instantaneous power. But they don't have any average power because they store energy in their magnetic fields, but then they return that energy to the circuit. Store, return, store, return. What do we decide? 100 times a second? But the average power is just RMS current. It's got to be RMS to work times R. Okay, we're going to do that. Now, what is the there it is. There's your RMS current, 1.372. You have to square it times 50. Okay, here goes. Square it times 50. Did you get 9406 watts? That's the average power. Now there's another equation for average power that goes like this. Let's see if we can check our work. This is called checking your work.
Something I wanted to ask. So
Yes.
if you just had a bunch of inductors and a bunch of capacitors, then your average power would just be 0, right? Since there'd be no R.
That is correct.
Okay. All right.
However, you would have current. You would have current. And you would have impedance. But it would all be on this vertical. There wouldn't be any, there's no resistor.
Yep.
Okay, we're going to do average power this way now. You take the RMS current. That's a good question, though. RMS voltage, cosine of your phase angle. Now, this thing here has got a fancy name. It's called the, I erased it. Dang, don't tell me. I can, the power factor. This thing here is called the power factor. Okay, here it goes. Now, the RMS current, we got it. It's right here. 1.372. The RMS voltage, see, that's the maximum there. The RMS is 70.71, I think.
Yes.
Do I need to explain that to
Yep.
anybody? Explain it? You're okay?
Vmax times 7 or 0.7071, right?
That's it. That's it. Times, uh-oh, I'm running out of space here. Times the cosine of phi. Well, we got the phi around here. Yeah, here we go. It's 14.1. So here we go. I'm multiplying all this together now. And I should get 9406. Let's see if I do. Okay, 1.372 times 70.71 times the cosine of 14.1. Boy, Jove, I'm getting an average power of 9409. Uh-oh, something bad happened. We got 9406 here. I must have rounded
Yep,
off
I got the same
something.
thing.
I think we're okay though. I think we just rounded off something. I don't know where, but I think we're all right. So we've got our average power. Now let's draw these waveforms. That'd be fun. I need a little room for that. You don't need any of this stuff. We'll get rid of that, and I'll draw the sinusoids here for you. Now we know we have a. Oops, we know we have a sinusoidal waveform that goes up to 100 and down to minus 100. It goes like this. It goes. There you go. Now that's the voltage. There's the voltage. And I tell you what this time is. It's 1/100th of a second. It's 0.01 seconds. Didn't we decide it's 100 cycles per second or 100 hertz? So for a complete pattern here, it does its whole thing in 1/100th of a second. Yeah, okay. Now this is an inductive circuit. Eli the Iceman. The voltage leads the current in an inductor. We're talking about an inductive circuit. There is no capacitor. So let me get my green, my green color here. Now, if the voltage leads the current, then the current must peak out later. How much later? What's phi? Did I erase it?
14.1.
It's not much. 14.1 degrees, right? So it's hugging this pretty close. Here, I'll kind of fake it here. There it is. It's 14.1 is not much, guys. It bottoms out just a tad later, not much. And then comes up here. There you go. Now we're looking at the current now. Now this is a different scale. See, this peaks out. Oh gosh, what did we get for the maximum current? I erased all the good stuff here. What was that?
We got 1.94 for the max current.
Thank you so much. See, the current, we'll put a little eye here, little green eyes on the current. This bottoms out at negative 1.94 amps, peaks out at positive 1.94 amps. Now the voltage, it peaks out at 100 volts, and it bottoms out at somewhere around negative 100 volts. They're awfully close together, but not quite. The voltage leads the current. See, it peaks out a little bit before the current does. Look here, this voltage comes down here and it crosses the axis here. That's earlier. The current doesn't cross the axis to here. If this is 180, no, that's 360 degrees. You could figure out the time to go 14, whatever you guys told me, 14 degrees. It's a simple ratio, 14 over 360 times 100th of a second. That'll tell you the time difference. Hey, we did that. We beat that horse to death, and we did the diagram, the impedance diagram. All right, well, let's do one more here. I have another one for us here. Before we do though, is there any comments or questions before we do another fun thing here?
What's the name of the diagram that is with the waves?
Thank you for asking. That's called the time domain diagram.
Okay.
You'll see that when you read your books about this stuff. This is the time domain. Now the frequency domain, I erased it, but that's your, when they talk about the frequency domain, well, they're talking about the
Jeff is asking if we are going to have to do graphs on the final.
no, you don't have to do any sinusoids, but tell Jeff that he's going to have to do an impedance diagram. Now, I've been doing
Okay.
them. I erased it, but we're going to do another one here in just a minute. But yes, impedance diagram. Now, I was thinking about your final. Here's something else you might want to practice on your final. And that's units. I think units are terribly important. Like, for instance, this thing here is called capacitive reactance. It's equal to 1 over omega c. What if I ask you on the final to show me the units involved? Well, you know what this unit is for capacitive reactance? It's ohms. Well, we're taking a break right now, just sort of like a commercial. And I'm giving you a little hint about the final because I want you to do well. And this is omega is 1 over seconds. And capacitance is coulombs per volt. Somehow you got to show me that this here is equal to ohm. Well, look, you see that coulombs per second? That's an amp. And you see that volts there? It goes up here in the numerator. And what you have here is volts per amp. Well, you know what a volt per amp is? That's an ohm, isn't it? Did you understand that? Yeah, you should be able to do that with
V equals
any-
IR and then just change it to
Yeah.
solve for R.
Exactly, V equals IR. You should be able to do any of our equations. Let's do another one, and then we'll have some more fun here. Let me make some room. But you should know the names. You should know the names of the things we've studied. We studied something here. We studied an equation like that. That equation even has a name. You should know the name of it. It's called motional EMF. That's the name of it. And you should know the units for all this, and you should be able to set them equal. Now, this here is voltage, so that's volts. B, that, you know what that is? That's magnetic field, isn't it? That's in Teslas. L is length, so that's meters. V is velocity, that's meters per second. Somehow we got to show that a volt is equal to Tesla meter times a meter per second. Well, Tesla is equal to a Newton per amp meter. There we go. So you could put that in, you'd have a Newton per amp meter, then you have a meter, then you have meters per second. Let's see. See what we want this to come out to equal volts. Well, we could get rid of one of these meters. We don't need both of them, so we get rid of that. You see that amp seconds in the denominator? See, an amp is equal to a coulomb per second. So an amp times a second is a coulomb. So what you have here is a Newton meter per coulomb. This thing is equal to a Newton meter per coulomb. And a Newton meter is a joule. So you got joules per coulomb. Well, that's what a volt is. A volt is a joule per coulomb. Ta-da! So there's some little hints to study on your final. Of course, it's open book, so you could just open your book and figure this stuff out. Okay, let's do another equation. Here we go. Another circuit. This time, I'm going to add the 20 microfarad capacitor. That's going to change everything now. It's going to change the by the way, back to that E equals BLV thing. Do you remember what we used that with? We had some kind of a circuit like this, some rails, yeah, some conducting rails, and we were moving a rod in a magnetic field. Yeah, that's it. Does that ring any bells? And see, the B was the magnetic field, and the L, yeah, you guys, we studied that stuff. L was the distance between the rails, and the V was the velocity that you're moving this conducting rod. And Lenz's law would tell us which way the current's going. Now, we're going to do this here in just a minute, but I want to see if we can figure out which way the current's going. The current is either going to go counterclockwise or the current is going to go clockwise. If you move this rod this way, it creates a current, but which way will it be? You have a 50-50 chance of getting this right. Let me pick on
I think it's, is it counterclockwise?
It is. You're absolutely right.
Okay.
The current will go this way. No. Which student was that?
That was me.
Was it Mohammed?
Logan.
Logan. I was going to say Logan. I should have. Yeah, Logan's right. It has to do with Lenz's law. Do I need to explain that, or should we move on?
I actually thought it was, I was trying to do the right-hand rule, so I thought it actually should have been different. Is it not? Because I thought make right-hand rule, and then wherever it's curving into is where the force is. So if the arrows are going into, shouldn't it be going the other way around?
If you put your thumb along the current,
yep,
you'll have magnetic field coming out. That will oppose this increasing magnetic flux going in.
Oh, okay. Okay, yeah. Okay, yep, you wanted to oppose it. Got it.
Lenz's law. Yeah, you really need to know Lenz's law. L-E-N, oh, brother. Lenz's law, there you go. Okay, now back to this one. Oh, gee, I erased all the good stuff. What was the capacitive reactance? And what was the inductive reactance? Help me.
Um,
The capacitance reactance is 79.57 ohms.
79
.57 ohms.
Did I get that right? 79?
And
Yep.
for inductor,
Good,
it's
good.
0.56.
And inductive reactance is 12?
12.56 ohms.
12.56. Thank you very much. All right, now I'm going to be quiet for another minute and a half. And I want you to draw the impedance diagram. And I'll be quiet. Go for it. Well, I'm going to draw mine to scale. Here goes. We need to have a 79 going down this way. So that'll make it about that long. And then we need 50 this way. I'm doing this to scale. And then we have, see that there's your XC. It's 79.57. And there's your R. And it's 50. And then this here is 12. To scale, that's pretty small. I can't help it though. That's what it is. There, I did those to scale. All right. And that's your impedance diagram, but we need the impedance. You have to subtract these, and what you'll get is XL.
67.01.
67.
Thank you. 67.01.
Yes,
Yep.
negative 67.
Yeah, it's a negative. Good going. What you have is XL minus XC,
Mhm.
and then we're going to get the impedance. Here it comes. There's your impedance. And what it is the square root of the XL minus XC squared plus 50 squared. Okay, well, I'm going to get the impedance now. All right, 6701 squared plus 50 squared. Did you get an impedance of 83.6 ohms?
Yes.
Yes, sir.
Yay, good. Now we're going to get the maximum current. Maximum current will be 100 volts. That's the maximum voltage. Divided by 83.61 ohms. It is 1.196 amperes.
Yep.
We got the max. Now, if you were asked for the RMS current, we can certainly get it. You just go 0.7071 times the maximum current, and that will be 0.8457 amperes. Yay, so we got the current. Now, they might ask you on your test for the voltages on these. So let's get that. Now the voltage on this inductor will be, and I'll tell you what let's do. Let's do the RMS voltages, because if we were in a lab, that's what you would measure to check your work to see if you did this right. We're going to get the RMS voltage. That'll be the RMS current times the 12.56. All right, here goes. I'm going to do it now. We're going to get the RMS voltage we think on that inductor. And I'm getting 10.6, I'm getting 10.62 volts. If you took your AC voltmeter, which measures RMS, and you put it on that inductor, it should say 10.62 volts. Now let's do the capacitor. Well, it's the same deal. The voltage on the capacitor will be the RMS current times got lost. Is it 79? It's 79. I can't read my writing. Is that 57? Is that what that is?
Yes, 79.57.
Thank you. 79.57 ohms. Here goes. Okay, take that times 79.57. I am getting 67 rounded off to 3. 67.3 volts on the capacitor. Okay, now let's do the resistor. Well, the voltage on the resistor is just V equals IR. So take your, and we're getting the RMS voltage now. That's what you would measure with a AC voltmeter. So we're going to take our current, RMS current times 50. And I did something wrong. RMS current times 50. I'm getting 42.3 volts.
Yes.
Now, if you add these three voltages up, the 10, the 42, and the 67, you will not get 100. Besides, they're all RMS anyway, and you won't get 70.71 either. But see, they don't add up like that. They're vectors. In fact, they're phasors. Here, I'll draw you the phasors. I got a little room here. See, you have a voltage phasor on the inductor. You have a voltage phasor on the resistor, and you have a voltage phasor on the inductor. This voltage phasor on the inductor is 10.62. Now I'm doing these with RMS. You can do them with a maximum or RMS. It's up to you. And on the resistor, it is 42.3 volts. And this is supposed to be the capacitor here. The capacitor is 67.3 volts. This is your the voltage phasors, and now they're spinning with an angular velocity of omega at 100 hertz. They're spinning around and around 100 times a second. And the omega is actually 200 pi, I believe. But if you were to add those as vectors, you should get the 70.71. Let's try it. If you take 67.3 and you subtract the 10, that will give you, let's see, 67.3 minus the 10.62. That'll give you 56.68. Square it, add it to 42.3 squared, take the square root, and what you'll get is the total voltage, which will be about kind of down in here. This is your total RMS voltage. Let's see what it says. Do that with me. Here goes, I'm doing it. Boy, Jove, I'm getting a total voltage of 70.7 volts. Well, see, that's the RMS voltage. That's the source. That's the source voltage. Well, now let's get the average power on this circuit. And then I think I'll be tired of it. I'm getting tired of this particular circuit here. I just need some room. Let me make some room here somehow. Okay, here we go. We're going to get the average power. Now we have two formulas for it. The easiest one is to take your RMS, square it on your current times R. Okay, here we go. Let's see. What is the RMS current? We had it there a minute ago. I lost it.
0.8457.
Good going. Good going. Square it, times it by 50. And here's what you'll get. I'm getting 35.76 watts. Uh-oh, I ran out of room to write my watts. Now we could check that. We have another equation for it. Let me squeeze that in here someplace. Here's some room. We'll do it here. Oh, wait a minute. I'm going to need this phase angle. Let me get that phase angle. Oh, gee, how do you go about getting that? No problem. You take 6701, I think. Yeah, and divide by 50. Take the arc tangent. You get 53.3 degrees. 53.3 degrees. All right, we're going to do it this other way, and we'll see what we get. We're going to take the root mean square current, which we have is 0.8457 amps. We're going to take the RMS voltage, which is 70.71 volts. And we're going to multiply by the cosine of 53.3 degrees, and we're going to see what we get. Go for it. Let's see what happens. boy, Jove, I'm getting 35.76 watts, the same one we got before. We found the average power of that circuit, didn't we? Now let's draw the waveforms.
What was the RMS?
The RMS current was 0.8457 amps.
Mm-hmm.
The
What was the
RMS
voltage?
The RMS voltage is 70.71 volts. See, that there's the maximum voltage.
Okay. Yep.
You with me?
Yep.
Yeah. Okay, now let's draw the waveforms, and then I'm going to be definitely tired of this. Got a little room down here. Now this circuit the capacitor is the boss. Can you see that? The inductor is pretty small. Here, this is your inductive reactance. Your capacitive reactance is much bigger. It's a capacitive circuit. How does that work? Eli the Iceman. The current leads the voltage in a capacitor. So let me draw that for you. Now I'm gonna draw the voltage in our circuit, and it's a sinusoid. It goes. Adam, I don't know how you translate. I don't know how you're going to translate that, but that's your problem. Okay. Now that's the voltage. Here, we'll put a little V on all that, shall we? Put a little V there. There's your voltage. There it is. You know what? It goes up to 100, doesn't it? And it goes down to minus 100. But now let me get my green color, and we're going to look at the current now. Oh, here it is. Now this says the current leads the voltage.
If we're mapping the voltage of the capacitor, then wouldn't the max voltage be 67.3, not 100?
No, this is the source.
Okay.
I'm mapping the source. We could do the capacitor and the inductor and the resistor, but this is complicated enough. It gets really messy. That's why they have these phasors. These phasors are so much easier to understand. But I am going to show you what the current's doing. Now the current is leading the voltage by how much? 53 degrees. Well, it's probably about like this. Peaks out, bottoms out. Here's the current. Can you guys all see this green current in the circuit there? There it is. This distance right here, or this time really, if you converted it to degrees, is 53.3 degrees. See, from here up to the top is 90 degrees. So I probably need to make it even bigger. I need to scoot it over just maybe 1/8 of an inch. But there's your current in your circuit, and it's leading the voltage. Look, it peaks out here. That's earlier. The voltage doesn't peak out till later. The current is leading the voltage by 53 degrees. It'd be fun to do the voltage on the resistor and the capacitor and the inductor separate, but that really gets messy. Okay, guys, we worked that problem to death, and I've given you some hints about your test. It's sad, but our time together is coming to an end. But it's been a pleasure.
I have one question.
Yeah.
So when you add up the max voltages on the resistor and the capacitor and the inductor, they add up to be over 100. Is that because they're maxing out at different times?
Oh, that's an excellent question. They don't add like scalars. They add like vectors. See,
Okay.
see, you know how vectors work.
Mhm.
Yeah, you know, you can have
They add up to a
yeah,
result.
like a
number.
5 there or better yet, have a 4 there and a 3 there. And when you add those, you don't get 7. You don't go 3 plus 4 equals 7. You get 3 plus 4 equals 5 because they're vectors. That was an excellent question. Well, it's been fun, and I've had so much fun, but I'm going to put my little arrow over this end in the lesson here, unless you have a last comment or question.
Okay, so the exam, you're going to,
Post Sunday afternoon or Sunday evening. I'll post the exam, and you have to do it Wednesday night.
and
Jeff
then
is
we print it off and then fill it out and scan it back into you.
Yeah, that would be great on Blackboard.
Okay.
You've done
Jeff is
it before
asking if
for
there
me.
will be.
I'm sorry. Say again.
Jeff is asking if there's going to be a review posted to Blackboard.
Oh, gee, Jeff, that's a great.
Or
That's a great
I know
idea.
that I think this was mentioned earlier, the possibility of like putting an old exam up there or something.
Yeah,
Well,
but also he's giving us so much time to do the exam too.
Yeah, you've
So-
got 72 hours, I think, and
Plus, it's open notes and open books.
it's
so.
open
Yeah.
book. And tell Jeff to, by all means, go over his 2 tests that he does have that he's taken. He's done. If I remember, Jeff did quite well. Go over your old 2 tests. That's a great idea, Jeff. Anybody else? Okay, I've got this over the little red button. Now, when I push this, it's all over.
Thank you, Professor.
Thank you, guys. Thank
Have a
you
great
very
summer.
much. I will. Thank you.
Bye. I'll see you.
Bye-bye.
I'll
It's been
Bye-bye.
see you in
fun.
the morning.
See,
Bye.
see you in the morning. You
Yeah,
got
I'll
it.
see you in the morning. All
Great.
right. Bye.
Bye-bye.